Hello, everybody. Welcome to the Thoughtworks Technology Podcast. I'm Rebecca Parsons, one of your recurring co-hosts, the Chief Technology Officer for Thoughtworks, and I'm joined by our co-host, Prem.
Hello, everyone. My name is Prem. As Rebecca said, I play the role of Tech Director. I'm one of the newer recurring hosts on this podcast.
And we are joined by two folks. Jayanta, would you introduce yourself first, please?
Yes. Hi, Rebecca. Jayanta here. I have been part of engineering for research team for last 2.5 years, mostly working with agent-based simulation models.
And Gautam, welcome.
Hi, Rebecca and Prem. My name is Gautam Menon. I'm a professor of physics and biology at Ashoka University in India. And I've been interested in epidemiological modeling for some years and have recently partnered with Thoughtworks with EFR.
So let's start with why you're here. We've got two different applications to talk about, but they are heavily related to each other. But let's start with EpiRust. Can you tell me what EpiRust is and what it does and why it's named EpiRust?
Sure, Rebecca. So EpiRust is agent-based simulation model, which is specifically designed keeping epidemiology as a domain in mind. As the name itself suggests, it has two parts, Epi and Rust. So Epi stands for epidemiology, and the simulation tool has been implemented using Rust language. That is why the name is EpiRust. So it is minimalist model of a city, or it can model multiple cities together, where we can analyze the spread of a disease and understand various different interventions and impact of these interventions on the spread of the disease.
And how did this idea come about?
This idea came few months before COVID itself started. As part of engineering for research team, we have always been fascinated with complex problems in the domain of complex systems. And to study complex systems, agent-based simulation models is one way. So while discussing these, we felt one of the biggest issue is epidemics. And specifically, if we talk about many countries in the world, there's this epidemic burden. In case of India, even that burden is there. And how we can study these epidemics with specifically using agent-based models. So that is how we started. And somewhere around when COVID-19 itself started, we thought of instead of modeling any disease, we started why not to model COVID-19 itself.
Got it. Excellent. Now, who is this primarily targeted towards? Is it epidemiologists? Is it end users like patients, doctors? Who uses this?
Specifically, EpiRust is targeted towards researchers, scientists, and policymakers as well. So, as we have been discussing about epidemics, right, which are complex in nature, to simulate epidemic, one has to have good understanding of what all different things related to an epidemic. So, if we talk about, say, COVID-19 specifically, once a person catches an infection, how long the person will be infected. So, we need someone from domain to understand these kind of intricacies. Once the person knows these details, they can run a simulation and understand the spread of disease. It is as well important for policymakers to make use of such tools so that they can understand, say, impact of lockdown. If a city is placed under lockdown for 30 days, instead if it is placed for 15 days, what it means, what will be impact on spread of disease. So such questions can be answered using such epidemiological simulation models.
And then the second part of this, BharatSim. What is BharatSim and how does it relate to EpiRust and how did it come about?
So BharatSim started really as a way of thinking about how to apply agent-based models to the Indian population. And agent-based models have been known, especially in disease, for a while. But there wasn't any work that looked at specifically a low and middle income country like India to try to accommodate the complexities of India, the extreme levels of social disparity, economic disparity, the complexity of Indian cities, the complexities of social interactions. So the idea was to try and be somewhat specific in the way we constructed that model, to make it general enough to look at a bunch of different diseases and to embed in it the levels of socioeconomic background, etc., that might be relevant to the understanding of the social determinants of disease. So I had been thinking about agent-based models in the Indian context for a while. And then serendipitously, I happened to meet people from EFR in Thoughtworks, in particular Harshal Hayat-Nagarkar. And we began to discuss work that had already been done at the Thoughtworks end with EpiRust and what I wanted to do with this very large-scale conception of what might be useful in the Indian context. So that's how the discussion started. And of course, it took on a life of its own. And BharatSim now is actually fairly different from the original conception of EpiRust.
And in what ways are they different? I mean, it sounds like the general problem is similar, but is it the specialization for the Indian market that distinguishes it, or are there other distinguishing characteristics?
Well, there's certainly that. And the thing is that BharatSim relies on a bunch of different components that come in together. And the first component is something called a synthetic population, which is a way of describing, in principle, every member of a population of a large Indian city like Bombay or Delhi or something. That, so-and-so is say 18 years old, goes to college, is about 5'11" tall, etc., is male. This is their home address. This is their work address. All of this is made up. It's synthetic, but it's made up in such a way as to reproduce the statistical properties of the population as well as we know them. So that's a very important part of BharatSim, of getting that part of it right. And that's where computer scientists outside of ThoughtWorks, the group of people I work with at my university, came to construct that population. Now, the BharatSim takes in that input in more classic agent-based model ways, and then runs that. It sort of asks, how does disease propagate in a population that is constructed in that manner, where you know where people are spread out in the city, that represents the spatial distribution of population within the city. And then you can ask whether COVID, whether TB, etc., how does disease spread within this, which is essentially what BharatSim does.
Yeah, so that was from domain context as well, right? Even at technical implementation levels, these two are different. So EpiRust is specific to epidemiology. It has been written with scale in mind. So with EpiRust, we can simulate population of 100 million plus on the go, and it is very, very fast. Whereas BharatSim shines specifically in the language of model specification. So EpiRust is more of a tool, but BharatSim is a framework. BharatSim has its own domain-specific language, which helps researchers to build their own model. So it need not to be epidemiology, but if someone wants to create a model which has epidemiology and impact of, say, disease on economy of the society, they can even write that using BharatSim. So in that way, BharatSim is more open. It's a framework as compared against EpiRust.
You mentioned, that you conceived EpiRust and BharatSim as part of this work that you're doing. Now, were there any solutions that were already there, and why was the need for you to build something from scratch?
Yes, definitely. So when we started our journey, we started with NetLogo. So NetLogo is time proven. It has been around for quite some years now. It has good UI as well. But biggest problem we faced with NetLogo is about scaling. We as well tried Gamma platform, which is JVM based platform specifically used for agent based modeling. But even with Gamma platform, we struggled a lot when we tried to scale beyond 10,000 agents. Our goal has always been to simulate at a large scale because we see since agent based models, the key factor, the most important part is emergence. And that emergence will be better justified if the scale is close to reality. So when we are talking about cities like Pune, Mumbai, where Mumbai has population which is close to 10 million plus people, roughly 12 million, we found it difficult to model such scenarios within Gamma platform or NetLogo. And that is why we thought we need our own tool, our own framework for modeling such high-scale, large-scale models.
And one more related question. We have mentioned agent-based models a few times. For our listeners, what exactly do we mean by an agent-based model?
Yeah, when we talk about agent-based models, what we mean to say is that we want to describe every unit of a population as an individual. These models are also called individual-based models, which means that they must account for the fact that you should just think of them as like real people converted to something that you can simulate on a computer. So all of the complexities of the family sizes, the genders, where people work, etc., are all going to be included in the specification of an agent. This is the most granular way of approaching how diseases spread. There are other approaches to diseases that sort of broaden these categories out, and just look at the numbers of people who are susceptible, the numbers of people who are infected, but don't break these up into further subcategories. You cannot get more granular than an agent-based simulation, and that's what makes it A, both powerful, and B, numerically and computationally complex.
And you had mentioned earlier, Jayanta, that one of the users for this would be policymakers. And Gautam, can you explain a little bit about how a policymaker might make use of either BharatSim or EpiRust?
Yeah, I can do that. Usually the problem confronting a policymaker is what's the sort of intervention to use, and how do you combine interventions to make them better and more useful in controlling the spread of a disease. So for example, should you have a lockdown? Should you combine a lockdown with mask wearing? What happens if 5% or 3% of people who are supposed to be locked down violate that lockdown? How does it affect the spread of the disease further? How does this affect economics? How does the fact that some people are just economically constrained to have to go out in the middle of a general lockdown and to work? What about people who are essential services people? What happens to them? These are questions. Should you close schools? Should you not close schools? Should you close offices? Should you close offices in some parts of the city but not in other parts? What should you do with public transportation? These are difficult questions to answer in general. And that's where models can really help, because they can help you explore counterfactuals. They can help you explore many different types of intervention. And all of this can be done with BharatSim.
I mean, this is really interesting, right? Are there real world uses that we have made with BharatSim and EpiRust?
With BharatSim, we have been advising some governments, some state governments in India, about school reopening, which has been a big issue. Indian schools have been shut for around 2 years, and they've sort of slowly begun to open up around the beginning of this year. Now, the question is, when is it safe to open a school, given that children under 18 in India have not been vaccinated? In fact, vaccinations for them started only in the very early part of this year. So then the question was, is there a difference in the policies that different states should adopt? What helps you decide? How can you look at schools embedded in communities where there's already a fair background of vaccination, a fair background of people who've already caught the disease? And then you can ask that if you've not vaccinated children, but you're sending them to school, where they could contact teachers and other school staff who may be carrying the disease, what impact will that have on the community? This again is a granular question. You can put, if children go to classroom, there's a certain level of mixing. There's not too much of mixing. You can say if children wear masks or don't wear masks, what happens? All of these questions you can now do very fast, because these numbers, if you just looked at a school in a community, you're simulating 20,000 or 30,000 people. You're not simulating in the millions. So that's a question which you can really explore the statistics of the situation, many different counterfactual scenarios, and then come up with advice that will be useful to a policymaker regarding this fundamental question.
So it's fair to say that this is an invaluable aid for policymakers when they're making those maybe not so popular decisions.
Absolutely. At least because then they can be backed up by the fact that, look, we have explored these different ways of intervening. And this seems to be the best way at this point that we know of. And in addition, if we did this, this, and this, then we could imagine having a stronger impact on suppressing the epidemic.
So let's get back to some of the technical foundations here. For EpiRust, why did you pick Rust? I know you mentioned, when you explored some of the existing frameworks, we were having performance issues. Was it strictly driven by performance, or were there other factors?
So a key factor definitely was performance. The major reason for choosing Rust for writing EpiRust is it's twofold. Rust is closer to metal. The performance benchmarks, if we compare, they are pretty close to C and C++ kind of languages. And we knew, right, we want to simulate that million scale, possibly 100 plus millions. And given these constraints, we decided we'll try and go as closer to metal as possible. Second thing is, Rust has concurrency in its DNA. The way Rust says it has fearless concurrency. And we definitely knew that we want to build a tool which can be used with lower population, maybe a researcher who is simulating it for a small town on a laptop with 10,000 population. It should work there. At the same time, if we want to run it for multiple cities, like 20 cities in India, which has combined population close to say 50 million, it should as well be able to run there. So we wanted something which can be easily made serial parallel version and as well as a distributed version. So that point, Rust did shine. C++ could have been one option, but as we know, right, with C++, memory management is developer's overhead. Developer needs to make sure that whichever memory is allocated has to be deallocated as well. In case of Rust, that overhead is taken care by Rust itself, which reduces many of the exceptions which comes with memory management, like segmentation faults. And all of these are converted into compile time errors, which expedites the development cycle.
And is BharatSim also, is the computational core underlying BharatSim, is that also in Rust?
No, BharatSim is written in Scala. We did think of Rust, but one key factor which changed with BharatSim is BharatSim had to be performant, had to be scalable, but at the same time, it was a framework. So the users who will be interacting with BharatSim will be writing their own model. BharatSim should have DSL, which should be easily understandable by developers, by researchers, and these researchers may not be from computer science background. So we wanted a layer of domain-specific language which can be easily understandable for the people from various different disciplines and domains. And that factor decided, with that in mind, we decided to go ahead with Scala instead of Rust.
And from the perspective of a researcher then, were we successful at creating a language that, Gautam, allows you to express the questions that you want to express? I mean, from what you talked about in terms of economic impacts and such, that feels like it's a pretty broad range of questions you would want to be asking. What can you tell me about that DSL?
I think that went very well, and what helped was the fact that both Thoughtworks and us had some experience in other alternative ways of doing agent-based models. For example, the Gamma platform or the CovaSim, which is another. And we knew what we wanted to do. We knew what we wanted to do that was different from what other people had done. We had some idea of the complexity that we wanted to accommodate that could not be accommodated in other ways of doing this. So working together with Thoughtworks was a real fun process in the sense of being able to interact, telling them what we wanted. They're coming back to say that, look, we believe we can do this, or this may be a little too hard. But I mean, they very rarely said this may be a little too hard. I think they really did. Really helped a lot. And in this discussion was extremely fruitful at both ends. So we really managed to create with BharatSim something that was, I think, unusual and unique.
Are there other uses that you see with BharatSim and EpiRust working together?
With BharatSim, certainly, I think the new frontier really is, for me, the social aspects of something like BharatSim. How do you model societies and societal behavior? And in the disease context, what are the socioeconomic determinants of disease? We know this both from the US and from India, that your socioeconomic status determines your propensity to contract COVID-19 in ways that are complicated. They vary across communities, they vary across different parts of the country in delicate ways. We don't really understand many of these. But with something like BharatSim applied to a US population or any population that you might choose to study, you can try to tease these factors out and ask, what is it about socioeconomic determinants that predisposes someone to disease, that predisposes a certain locality, an area, a group to diseases spreading faster there? And other questions about society, that society economics, the interplay of that with just health, public health in different contexts. That's something that has not been explored sufficiently. And with BharatSim, I think we really have a chance to look at that completely afresh and see where that leads us.
Yes, and on the EpiRust specifically, EpiRust has been targeted only towards epidemiology. But what we have been working is various different scales. So when we started EpiRust, we started with Pune city, which has a population of 3.2 millions. Then we slowly move ahead to Mumbai, which is 12 millions. Right now, we are at a stage where we can simulate 100 plus millions. The goal for EpiRust, which we have kept, is going beyond 100 plus millions and possibly to a billion scale. By doing that, we as well want to compare the impact of scale given this specific model and how the outcome changes. So I guess which would as well be important for policymakers, right? If a policy which is prescribed for a small town may or may not be applicable as is for larger cities. That can be one example.
So what you're saying is we are very close to even covering the world population, which is approximately 8 billion at this point in time. So we can do simulations for pretty much people across the globe or even the entire globe.
Definitely that's on the agenda. Right now we are at 100 million. Very first goal is reaching 1 billion and definitely moving to 8 billion.
Yeah, to sort of expand upon that a little bit. I mean, you can get to larger numbers, but it depends upon the detail at which you want to describe your population. If there are 100 or 200 different attributes that you want to include, then you have to trade that off against the sort of numbers that you can simulate. Some questions are perfectly well answered with 20,000 or 200,000 or 2 million, etc. So those questions should be answered at that level. But really to sort of show our numerical chops, our computational chops, maybe it would be nice to try something at the level of the whole of the population of India at 1.4 billion or the population of the world.
I had a question about that. I mean, how are you simulating the data, or where are you getting your data from?
That goes into the description of the synthetic population. And for that, that's a different set of techniques. These are mainly AI ML techniques applied to information that you get from surveys. There is public information available from surveys about that tell you about demographics. And then you have to figure out a way to extend that across the whole population. You have state-specific information, which you can then apply to each state. And you can try and bootstrap that into areas where you don't have enough information, but you do have some level of information, some partial information. That is a challenge. Getting a good synthetic population is a challenge anywhere. We hope to sort of incrementally make progress with that until we have better and better synthetic population. Already by comparing the sort of averaged properties of our synthetic population with what we know from large-scale surveys and census information, we know that we're not doing too badly. But that still is a frontier. That's a whole different area of improvement that we'd like to spend more time on in the future.
Where do you see going from here? Are there any specific next steps you have in mind?
With BharatSim, we'd like to expand the range of diseases that we look at. We sort of thought initially of BharatSim's application was really for COVID-19, and we were funded initially to think about COVID-19 in India, with a special attempt to try and integrate socioeconomic determinants into that description. But there's many other types of diseases, neglected tropical diseases, for example, or diseases that are transmitted by vectors, malaria being one, dengue being another, chikungunya being a third, all of which afflict countries like India as well as countries that are in the equatorial belt. Extending these methods to those problems would be very important for the country, very important source of information for policymakers. That's certainly a direction in which I'd like to take BharatSim in the future.
And EpiRust?
Yes, and on EpiRust front, we have been trying to do various different analysis methods on the outcome of EpiRust simulation. So one such thing is sensitivity analysis, right? If there are dozens of input parameters and which one matters the most, deciding the output. At the same time, stability analysis. So how stable is my solution? So we have been trying to understand various such analysis methods and understanding simulations better.
And in terms of EpiRust in particular, you've mentioned that it is specifically designed for questions around epidemiology, and yet simply being able to do agent-based simulation in that 100 million agent range, how applicable do you think your strategies for being able to scale to that kind of population? How much is that tied to your implementation for epidemiology specifically?
So with EpiRust, when we say it's 100 million plus, what we are trying is model different cities. So imagine if we talk about Mumbai against Pune. Mumbai is very densely populated, whereas Pune is not as dense as Mumbai. So ideally, the data of these two cities is different. And when we run EpiRust for various such different cities, the outcome of these cities differ from each other. At the same time, when COVID started in India, we saw in the first wave of COVID, many people migrated from Mumbai to their own hometowns, their different cities. So even such migrations, it has huge impact on spread of disease. So earlier, in few places of India, the COVID may not have been there. These when many such people at such scale moved from one city to another, it could again trigger wave at these different locations. So when we simulate 100 plus millions of people with so many different cities, we can study such phenomena that uh, at given time, X number of people leave a specific city, and then next specific time they enter these different cities. So may few of them might already be infected, and then the interactions in their hometowns, how it causes spread in these different areas.
And I suspect those socioeconomic factors that you were mentioning earlier, Gautam, play into the realities of those migrations. Some people are more able to migrate. That's one of the things that we've seen in the U.S. is, many people are now living in places because they could afford to get out of a place like New York City.
Yeah, so that again is something that we need to worry about, because in India you do have these large-scale migrations. People migrate from villages in order to work in cities. And at the time the big lockdowns started in India, we had people moving back to the cities, being unable to do that because they were under a lockdown situation, then being released across a period of a few months, going back, and then potentially, as Jayanta said, transferring diseases to places that hadn't seen it before. So all of this complexity, one needs to think about the problem at the level of individuals, which really is what EpiRust and BharatSim are both about, which is why agent-based models are important, because they can accommodate this level of complexity.
And if you were talking to an aspiring young scientist, are there recommendations you would have to them on how they might get involved in some of this work? I mean, clearly, being able to study diseases like malaria and dengue, as you mentioned, there's got to be a degree of satisfaction. But what does it take to really get involved in such studies?
We're seeing a lot of interest from, I work at an primarily undergraduate university, and there's a lot of interest from students, especially post-COVID, in sort of coming to terms with epidemiology, understanding it, seeing if they can contribute in some way. I think everywhere people have become more aware of the importance of public health and the need, especially if you're academically inclined, the need to look at academic and scientific tools in different ways to see if they can be of help, if they can be of use at all. And I think one interest with BharatSim is the fact that it combines both the sciences and the humanities, social sciences together in an interesting way. And that, very few subjects really can do that. Public health can. And here's an approach, a numerical and computational approach to public health that ties all these different elements together in interesting ways. And I think that catches people's attention. And there's certainly been a lot of interest in BharatSim for that reason.
And are you looking at broader collaborations in further developing BharatSim?
We're always looking for collaborations, and there are many people who are interested who are in touch with us. And certainly one interest would be to take BharatSim outside India, to look at, for example, different countries across the world, Malaysia, countries in South Asia and Southeast Asia, where all of us face similar problems. You need different synthetic populations, so you need to develop a synthetic population for those countries and then answer questions. Then the second thing is, can we push BharatSim in areas where it hasn't been used before? For example, in understanding vaccine trials, or modeling the effects of vaccines, or multiple strains of, for example, Omicron, as the world is seeing now. Whenever you have an infectious disease that changes dynamically, like COVID-19, these questions will come up and they'll need to be answered in real time. And BharatSim offers you a way of doing something like that, of really putting in the complexity as and when you understand it, and then asking what are the impacts of that in the future.
And Jayanta, same question, but a computer scientist who wants to get into this kind of work, both the large-scale simulation and the computational science nature of this. I mean, I've done in my career a fair amount of work in computational medicine and computational biology, and to me that interdisciplinary aspect is of interest. But how would you counsel a brand new thought worker on how to get involved in work like this? What kinds of things what kind of tools do they need to bring to such work?
Yeah, definitely. So while building such large-scale simulation platforms and frameworks, right, I think understanding of data structures and algorithms is pretty fundamental. At the same time, understanding high-performance computing setups, some bits levels of DevOps, and as well as various different languages such as C++, Rust in this case is pretty important. We are very happy to have collaborations, and for the same reason, EpiRust is already open source.
And how long did it take you to learn how to speak each other's languages? I distinctly remember a conversation with a molecular biologist, and he was using the word vector that you used earlier, Gautam. I said, well, I know two definitions of vector, and I don't think he means either one of those.
I think it did help, certainly from our side, Sarjan, that Harsha had some experience, that already the EpiRust people did have some initial grounding in understanding the basics of infectious disease modeling. And we had on our side computer scientists like my colleague Debayan Gupta, who was able to understand and speak the language that Thoughtworks was comfortable in. So I think both of us had to move a certain distance from our comfort zones. But I think Thoughtworks did try to make it easy for us, and we've tried to be as clear and as jargon-free as possible in our interactions with them. So we both worked hard at it, and I think it worked out finally.
Well, thank you, Gautam and Jayanta, for joining us today for this fascinating exploration of public health policy, epidemiology, and large-scale agent-based simulation. Thank you very much for taking the time to talk to us, and thank you, Prem.
Thanks, Rebecca. Thanks, Prem.
Thank you, Rebecca and Prem.